So I'm going to talk about limiting reactant. And theoretical yield. I think why I skipped this, because technically there's another component called percent yield. And I don't think that's on the worksheet, but maybe we might as well talk about that as well. And so what I want to say is you use the limiting reactant to, anyways, use the limiting reactant to calculate everything. Okay. Okay. So I'm going to use a metaphor. I'm making bicycles, okay? And here's my frames. I'm in a bicycle factory. I got this many frames. And I got and I have that many wheels. And I have that many whoops. That was too many. And I have that many handlebars. Okay, how many bicycles can I make?
2.
Yeah. So if I'm making bicycles, these are the worst bicycles you've ever seen. But here we go. A really important concept to put a star by this is to use the limiting reactant to calculate everything. But first I'm doing a metaphor. So we have all these parts and I'm making bicycles. And so somebody said, hey, with those parts, you can make 2 bicycles. And I'm going to have some stuff left over, right? How many frames will I have left over?
1.
1 frame, and I'm going to have, well, gosh, I'm going to have 4 wheels left over, yeah? Now I can't use to make a complete bicycle. All right. So in this example, the handlebar is what we call the limiting reactant. And the wheel and the frame are what we call excess reactants. We had more frames and wheels than we could use. Okay. So let's continue. So the limiting reactant gets completely consumed, right? So how many handlebars were left when we were building bicycles?
0.
There were 0. And the limiting reactant determines the maximum amount of product. All right. So, and the way to do this is, so kind of the steps for this is, I'm going to put step 0 again, which is have a balanced equation. And then the first step is to use each reactant to determine the amount of the same product that will form. And this is actually, that's the hardest work. This is actually 2 equations. Or more, I suppose, if you had more than 2 reactants. But once you've done that, the reactant that made the least is the limiting reactant. So let's continue. So steps, balanced equation, use each reactant to determine the amount of the same product that will form. Once you've done the first step, then the other steps are just an analysis of the calculations. And so from looking at the calculations here, whatever one made the least is the limiting reactant. And that amount is actually what we call the theoretical yield. And so we should also mention the theoretical yield. The theoretical yield is the maximum amount of product that you can make. Okay, I'll put that over there. Okay, so theoretical yield is the maximum amount of product that you can make. Let me, just for a second, let's go back to the bicycle factory. What was the maximum amount of bicycles that we could make?
A whole 2?
Yeah, so 2 bicycles, that's my theoretical yield. I suppose if, you know, the bike mechanic really cranks on one of the handlebars and breaks it, then I don't get to actually make 2 bicycles. I mean, I only get to make 2 bicycles if I'm successful in putting them together. Does that make sense? But at best, I could make 2. I can't make 3. I don't have any. I ran out of handlebars. My limiting reactant is gone. I can't make any more than 2. Okay. So let's do that with a chemical reaction. Let's go back. I'm going to go back to the Haber process. Nitrogen plus 3 hydrogen goes to 2 ammonia. So if 2.5 moles of nitrogen react with, let's say, 5.7 moles of hydrogen, comma, how much NH3 can be made? Question mark. And what is the limiting reactant? Question mark. All right. So this example is a little bit more simple, but we're just gonna go from moles to moles. So step 0, balanced equation. That's above. Step 1, 2 equations to find product. So here we go. I have 2.5 moles of nitrogen, and how many moles, according to 2.5 moles of nitrogen, how much ammonia could be made? What's the mole ratio? What's the balanced equation tell me about the mole ratio between nitrogen and ammonia? You guys are so quiet. We were doing this earlier. Nobody? Okay.
2 to 6? No.
You look at the coefficients here.
Oh, is it 1 to 3 is 2?
Now just look at nitrogen and ammonia. We're going to find product. So this is a product. These are reactants, right? And I'm going to use my handlebars and frames to figure out how many bicycles, right? So what's my what's my nitrogen ratio to ammonia? Let's call nitrogen the handlebars. How many handlebars?
One, right?
One handlebar to how many? I guess it's not called handlebars, but how many nitrogens will make how many ammonias?
One.
Okay. Yeah, so someone's texting 1 to 2. Where's the 2 have to go? Where's the 2 have to go?
Up top.
Yeah.
Up
2
on
moles
top.
of ammonia, 1 mole of nitrogen. Okay, well, that's pretty easy. 2 times 2.5 is 5. Well, actually, let's make it 2 sig figs. 5.0 moles of NH3. Okay, so that's the first equation. I'm going to call that A. Let's do the second equation, B. I also have 5.7 moles of hydrogen. 5.7 moles of hydrogen. What's the ratio of hydrogen to ammonia? Nobody?
Is it 3?
Yeah, there's a 3 for the hydrogen. 2.
2?
3 to 2. Okay, so where does the 3 go?
On the bottom?
Yes. 3 moles of hydrogen on the bottom, cancel. And 2 moles. Maybe I should cancel out units here too, right? Moles of hydrogen with moles of hydrogen. Just like above, we canceled moles of nitrogen with moles of nitrogen. Okay, so then I'm going to have, this one's kind of more complicated. I need my calculator. So 5.7 times 2 divided by 3, and I get 3.8 moles of ammonia. Okay, so this one's kind of cool, actually. If you look at this, I had more hydrogen, but it made less ammonia. Why is that? Why is that? I had more hydrogen than I had nitrogen, but it made less ammonia.
Because you still have the limiting.
Yeah, so he's saying, so this is less. So now we're doing step 2, is basically compare, right? So this is less. So go back to hydrogen. If that's less, then hydrogen is limiting, right? Another thing we could say, so we can't make, let me cross this one out. We can't make 5 moles of ammonia. Why not? I mean, think about my bicycle factory. I can't make 3 bicycles. I'd like to make 3 bicycles. I can't, right? I run out of handlebars. So I can't make 5 moles of ammonia. I can only make 3.8. So hydrogen's limiting. The other thing we can say is 3.8 moles of ammonia is the theoretical yield. That's the maximum that we could make. Yeah? Okay. And so someone was saying, yeah, you couldn't, because you're dividing by 3 here, you can't make, you make a lot less, right? It's because of this, it's because of those mole ratios. They're super, super important. So this example is the easy example because I just did moles to moles. I could make this more complicated by giving you grams. Are you guys ready to see one of those?
Yeah.
Okay. The other thing is, let me be clear too. We can have different products. So let me use a completely different situation. How about calcium hydroxide plus 2 HCl goes to 2 water plus CaCl2. Okay? And if let's make them the same amount. If 10.0 grams of calcium hydroxide react with 10.0 grams of HCl, comma, how many, to make it easy, let's go to water. I mean, I could choose either product. How many grams of water can I make? Question mark. Okay. So you guys ready? So it's the same process, right? So step 0, balanced equation, done, right? Step 1, 2 equations. I'm going to take the 10 grams of calcium hydroxide. What's the molar mass of that? So I'm going to cheat. Oh, come on. Why isn't it? No, it's not working. What's the molar mass of calcium hydroxide?
40.1.
40.1 is just the mass of calcium. You guys want to see all the work for calculating the molar mass of that? Okay, fine. Let's do that. Okay, let's find calcium hydroxide. So calcium hydroxide has 1 mole of calcium, which is, I think it's 40.08, and 2 moles of hydrogen. Is that right? Because the 2 distributes, yeah? And 2 moles of oxygen. So 2 moles of hydrogen is 2.02. 2 moles of oxygen is 32, right? 2 times 16. 2 times 1.01. Okay. So if I add all that up, I get 0, 1, 74. Is that okay? Let's also find HCl. HCl is 1 mole of hydrogen and 1 mole of chlorine, which is 1.01 plus 35.45, which is 36.46. Yeah? Is everyone on board with what I just did?
Yeah.
Okay. So I haven't done the 2 equations yet. I've just calculated the molar mass. Now, equation 1, or A, let's make the first equation. Let's take the calcium hydroxide. 10.0 grams of calcium hydroxide times 1 mole of calcium hydroxide to 74.10 grams. Let's cancel out the grams. Okay, what's the mole ratio between calcium hydroxide and water? You guys see that? Anybody? Ramon has unmiked? No?
Yeah.
What's the mole ratio of calcium hydroxide to water?
1 to 2.
1 to 2. Where's the 2 go?
On the bottom?
It's 2 moles of water. I want actually on the top. 2 moles of water, 1 mole calcium hydroxide. Okay. And then we could just find the moles. Let's just find the moles. Okay. And I got to do it with the second equation. B, 10.0 grams of HCl. These are actually going to be pretty close to each other. Times 1 mole of HCl, 36.46 grams. And then what's the mole ratio of HCl to water? Oh, yeah, there it is. HCl to water, what's the mole ratio?
2 to 2.
2 to 2. Let's put that, doesn't matter. 2, 2. 2 moles of water, 2 moles of HCl. Okay, and whatever that is. Okay, so then it's time to do the calculator. So the calculator, the calculator says for the first one, 10 divided by 74.1 times 2. So this one here is 0. Let's say 3 sig figs. I'm going to put 4. 0.2699 moles of water. And then this one here, let's see what this one does. 10 divided by 36.46, well, times 2 divided by 2 is just times 1. And that is 0.2742 moles of water. Okay, so which one makes less? Yeah, so Shams is saying the top. This one here is the theoretical yield. Forget about that. That bottom one was just a waste of a calculation. Well, we needed to see that it was more. And then this here is the limiting reactant. Is that okay? Hold on a second. He's got a good question. So for each reactant, we went from grams of reactant 1 to moles of reactant 1 to moles of product. And here I'm going to say product 1 because we actually have 2 different products, right?
Yeah.
So this was A, right? We went from grams of calcium hydroxide to moles of calcium hydroxide using the molar mass. And then once we had moles of calcium hydroxide, we canceled the moles of calcium hydroxide and got moles of water. Yeah?
Yeah, good.
Okay. And then, so we also did that for the second one, right? We went grams of reactant 2 to moles of reactant 2 to moles of the same product, product 1. These have to be the same over here, yeah? If they're not the same product, then I can't compare it. So let just go back to the equation for a sec. If I had used the calcium hydroxide to calculate calcium chloride and used the HCl to calculate water, then I have 2 different things. I can't compare them. But what I did is I used both of them to calculate water. Then I could compare and said, aha, this one makes less water than that one. Yeah? Okay. So technically we're not done. So then the maximum amount of water, I want to go to grams, right? So I'm going to take this value here, 0.2699 moles of water, and I'm going to multiply by, what's the molar mass of water? Anyone remember? 18.02 grams. We did that from before, right? I'm cheating. So 0.2699 times 18.02, and I get, well, this reaction, I have 10 more minutes, but that's probably good. So from this reaction, I can get, and now I want to look at sig figs. This was 3 sig figs here. So actually, I can make 4.86 grams of water. That's the maximum.